Somewhere under the ocean, a thread of glass thinner than a human hair is carrying a video call across the planet. Inside it, there is no electricity. There is only light, bouncing, trapped, and racing forward at nearly the speed of light. This single fiber can hold thousands of conversations at once, and it never spills a single drop of that light. Let us slice one open, slow it all down, and watch exactly how it works. For a long time, we sent messages as electricity through copper wires. But electricity fades. Push it down a long copper line, and the signal grows weak, smeared, and slow. Copper also leaks energy as heat, and it picks up noise from everything around it. Engineers wanted something faster, cleaner, and far thinner. The answer was hiding in plain sight. Glass. Send your message as light through glass, and the rules of the game completely change. Slice the fiber open, and you find two layers of glass, one nested inside the other. At the center is the core, a strand often thinner than a hair. Wrapped tightly around it is the cladding, a second glass made with a slightly different recipe. Around that sits a soft plastic coating for protection. The core carries the light. The cladding is the wall that keeps it inside. Together they form a pipe for light, with no moving parts at all. Now send a beam of light into the core. If you aim it straight down the middle, it simply travels forward. But fire it in at a shallow angle, and something strange should happen. You might expect the light to leak out through the side wall and escape into the cladding. In an ordinary pipe, it would. Yet in this fiber, the light hits that boundary and bounces straight back inward, as if the wall were a perfect mirror. The trick has a name: total internal reflection. Light bends when it crosses from one material into another, and it bends based on how fast it can travel in each. The core is built so light moves a little slower inside it than in the cladding. When a ray strikes the boundary at a shallow enough angle, it simply cannot cross. Instead, all of it reflects back into the core. Nothing leaks out, the light is trapped, and it keeps moving forward. So the light does not travel in a straight line. It zigzags, bouncing off the walls thousands of times every meter, yet losing almost none of itself. Picture skipping a stone that never sinks, gliding forever across the surface. Because the glass is astonishingly pure, the beam can race for tens of kilometers before it noticeably dims. The cable can even bend around corners, and the light simply follows the curve, reflecting its way along the path. But light alone is not a message. At the sending end sits a tiny laser, or an LED, that can flash on and off astonishingly fast. Your data, every photo and word, is already a string of ones and zeros. The laser turns that code into light. Flash on for a 1. Stay dark for a 0. It can blink billions of times each second, far faster than any eye could ever follow, pouring the message straight into the glass. Down the fiber the pulses fly, a stream of bright flashes and dark gaps, holding your message in their rhythm. They move at roughly 200,000 kilometers every second, about 2/3 the speed of light in empty space. In a single blink, a pulse can cross a city. Many separate signals can share the same strand, never colliding, because light does not bump into light. The glass stays cool, and the flood of data just keeps flowing. Here is where it gets clever. You can send more than one color of light down the same fiber at once. Each color, each wavelength, carries its own separate stream of pulses, and they ride together without ever mixing. This is called wavelength division multiplexing, WDM. Imagine dozens of distinct conversations, each painted a different shade, sharing one thread of glass. At the far end, a prism-like device fans them back apart, so every color can be read on its own. No glass is perfect. Over very long distances, even this pure light slowly fades. So along the route, the signal passes through amplifiers. Some are special stretches of fiber, doped with a rare element, that soak up energy and pour it back into the passing light, brightening every pulse without ever turning it into electricity. Under the oceans, these boosters sit spaced along the cable, quietly lifting the weakening flashes so the message can finish its journey across the world. At last, the light reaches the other end, where a photodetector waits. This small chip does the reverse of the laser. It watches the stream of flashes and dark gaps and turns each one back into electricity. A flash becomes a 1, a gap becomes a 0. The original code is rebuilt, pulse by pulse, and handed to a computer. The light has carried your message across continents, and here it quietly becomes data again, ready to fill your screen. So follow the whole chain once more. Your data becomes 1s and 0s. A laser flashes them into the glass core as pulses of light. Total internal reflection traps that light, bouncing it down the fiber without escape. Different colors share the strand, multiplying the message. Amplifiers revive the pulses across vast distances. And at the end, a photodetector turns the light back into data. Copper carried a trickle. This thread of glass carries an ocean, all on a beam of light. A single strand of glass, thinner than a hair, quietly holding the whole world together with nothing but trapped light. The next time your message crosses the planet in a heartbeat, picture it. A tiny flash bouncing down a river of glass, never spilling, never slowing. Now you will know the exact path it took. Thanks for watching The Cutaway. We will see you at the next slice.